All right, let's get right into it. We've known for a long time that glaciers are melting, but it turns out they're disappearing way faster than even our best computer models have been telling us. And the really big question has always been, why? Well, it looks like science is finally catching up, and the answer has been hiding in plain sight. And, believe it or not, in plain sound. You see, everything we think we know about future sea level rise and freshwater supplies, it all depends on these scientific models that predict how ice melts. But here's the problem. They have a critical flaw. They've been consistently and seriously underestimating the melt that's happening in the real world right now. They're missing a huge piece of the puzzle. So when we say wrong, how wrong are we talking here? Is this like a small rounding error, or is it something way, way bigger? Yeah, this is where it gets pretty wild. A huge study found that the melt rate scientists were actually observing in the field can be 10 to 100 times greater than what the standard models predict. Let that sink in. That isn't a small mistake. It means we've had a fundamental misunderstanding of the physics of what's going on. So what in the world could cause such a massive gap between theory and reality? Well, the answer isn't some new mysterious force. It's actually a property of the ice itself, something we've known about for a very long time, but just never plugged into the equation. It's a property you can literally hear. See, it all comes down to how glacier ice is actually formed. It's not just regular frozen water like you'd get from an ice cube tray. It's more like a time capsule full of ancient atmosphere. And that single fact, well, it changes everything. The whole process starts with snow, centuries of it just piling up layer after layer. The immense weight from the top layers compresses the snow below, squeezing it into incredibly dense ice. But as it squeezes, it traps little pockets of air. Eventually, those pockets get sealed off completely, forming these tiny, highly pressurized bubbles of ancient atmosphere. And we're talking about a lot of trapped air. Glacier ice is about 10% air by volume. In a single cubic centimeter, that's about the size of a sugar cube, there are around 200 of these little bubbles. And they're not just sitting there. The pressure inside can be up to 20 times the atmosphere around us. So when the ice finally melts, they don't just gently release the air. They explode. They pop. It's what creates that famous crackling sound you hear in glacial fjords. For the longest time, scientists just thought of this popping sound as, a cool side effect. But then some researchers started to wonder, what if that noise wasn't the side effect? What if it was the main event? So they set up this really clever experiment to figure out what these bursting bubbles were actually doing. They basically created a tale of two ices. On one side, you have perfect, clear, bubble-free ice. This is the idealized stuff that our climate models have always assumed glaciers are made of. And on the other side, you have the real deal, actual glacier ice, taken from Greenland, cloudy and packed with all those pressurized bubbles. They put both types in saltwater tanks and just watched what happened. And the results? They were just astonishing. The real glacier ice didn't just melt a little faster. It crushed the bubble-free ice on every single metric. The melt rate was higher, the plume of meltwater rising from it was way faster, and all that activity created a ton more turbulence and kinetic energy in the water, which, you guessed it, causes even more melting. I mean, just think about this for a second. The simple presence of these bubbles, something our models have always ignored, more than doubled the rate of melting. Right there. That alone tells you the models have been starting from a fundamentally flawed place. But it gets even crazier. Those bursting bubbles acted like thousands of tiny jet engines, constantly stirring the water right at the edge of the ice. That created a plume of meltwater that was 6 times faster than the one from the clear ice, which means it was dragging much more warm ocean water up against the glacier face. And here's the kicker. When they calculated the total kinetic energy being released, the plume from the real glacier ice generated 20 times more energy. It's like comparing a gentle, lazy river to a raging waterfall. It's a completely different level of power. Okay, so this isn't just some neat thing that happens in a lab tank. This corrosive fizz effect, as they call it, has huge implications for what's happening out in the real world. In fact, it helps solve a mystery about the very shape of glaciers that has puzzled scientists for years. You see, the old models predicted that glaciers should be undercut. Basically, they should melt fastest deep underwater, creating this kind of overhang at the bottom. But when scientists actually went out and measured them, they often found the exact opposite. They were overcut, melting faster near the surface. The theory and the reality just didn't match up. And the bubbles explain why. The explosive energy from the bursts happens at all depths, churning the water everywhere. But the buoyancy, the lift you get from all that rising air, is way more powerful in the top 40 meters or so. This extra energy near the surface supercharges the melting right at the waterline, carving out that overcut shape we see in the real world. The puzzle was finally solved. So, okay, bubbles make glaciers melt faster and change their shape. Why should any of us care? Because this discovery fundamentally changes the timeline for one of the most vital resources on our planet, fresh water. Think of glaciers as Earth's natural water towers. For thousands of years, they've captured snow in the winter and then slowly, reliably released it as meltwater during the hot, dry summer months. They feed the rivers that literally billions of people rely on to live. And this brings us to a really important idea called peak water. It's a little counterintuitive. As a glacier first starts to melt and retreat, it actually releases more water for a while because you're draining centuries of stored ice. But that bonus can't last. Eventually, the glacier shrinks past a tipping point, the runoff hits a maximum, and then begins a long, steady, and irreversible decline. You can see the life cycle here. You go from a stable system with a reliable flow to a temporary surplus as the glacier starts to go. But that extra water comes at a price. Once you hit peak water, the system flips. You enter a new reality of less and less water, year after year after year. The water tower is officially being drained. And this is not some far-off, distant future problem. It's happening right now. Places like the Andes are already past peak water. They're facing a future where a shrinking water supply is colliding with growing cities and farms. The Swiss Alps are getting close to their peak, and the Himalayas are not far behind, putting the water security of billions of people at risk. So, uncovering this hidden engine of glacier melt, it pretty much forces us to rethink everything. It injects a whole new level of urgency into how we plan for our future when it comes to water. It's really an amazing story when you step back. We started with a microscopic bubble of air trapped in ice centuries ago. And we followed that thread all the way up to its massive impact on our planet's water supply. It just goes to show how a tiny detail, something overlooked for decades, can completely change our understanding of a giant planetary system. And all of this leaves us with a really big and, frankly, difficult question. We now know for a fact the ice is melting much, much faster than we thought. The water towers are cracking. So the challenge ahead for all of us isn't just about the ice anymore. It's about how we're going to manage the water that's left.